Good afternoon. Earth History class, this is Chapter 6. This is an important chapter for the people that are in lab, and I'm going to break this up into 2 video lessons. I pretty much have to because there's so much material. So this is going to be called Chapter 6 Video Lesson Part 1, and I may just leave this, it will be on Canvas. I may just tell you guys to watch these video lessons on your own and not do any of Chapter 6 in class. That's a possibility because it's not so important for the people that are not in lab. Okay, so let's begin. All right, sedimentary rocks form from the lithification of sediments. In other words, how do sediments become solid rock? And the answer is, well, the sediments have to be buried first. Burial, meaning that new sediments are deposited on top. They therefore are compacted and squeezed closer together, and then you need to have some kind of natural cement come through, like quartz or calcite, for example, or iron oxides, that glue the sediments together. Second bullet there, pretty important. Sedimentary rocks only form in the upper crust. Okay, they don't form in the lower crust. They're forming in the upper crust only because that's where weathering happens, and they are covering older igneous and metamorphic rock. All right, next topic. Different color. I've tried to change my colors out with different topics. Next topic here, depositional environments. So what does that mean? It means what was the specific environment like where that sediment was deposited. Okay, so we're going to look at things like what minerals are present. Okay, if it's calcite, for example, then that's likely a limestone, and that was a marine environment, meaning ocean water. We're going to look for bedding, meaning layers, thickness of layers, that kind of stuff. We're going to look for any fossils, and then we're going to figure out what kind of animal or plant we have here and what kind of time period did it live in. We're going to look at the grain size. Are they small, large, or in between? And we're going to look at sedimentary structures. We're going to learn the basic sedimentary structures in this video lesson. So we can tell, for example, if this location was a desert in the past, or a beach, or a braided stream in the mountains. We can tell if it was a shallow marine environment or a deep marine environment. All right, so some other interesting tidbits here. Red rocks are likely continental rocks. And why do we say that? Because oxidation has occurred, okay? So meaning that your iron is going up in charge, like from a 2+ to a 3+, for example. In other words, your iron and or magnesium-bearing minerals in that rock, they were exposed to oxygen in the air and oxidized. So red rocks likely were in a continental depositional environment. Green rocks, on the other hand, likely formed in a marine environment because green is a reducing environment, as in your Fe2+ going down, being reduced to just Fe+1. So green rocks are likely marine, indicating a reducing environment. All right, we have to move to the next board. Getting all my markers together. Okay, so I'm going to sit here. All right, in green. Now we're in green, so we're on to a slightly different topic. Just some interesting things about what the sedimentary rocks tell us about what the environment was like in the past. Okay, so detrital sedimentary rocks, and those are sedimentary rocks that come from pre-existing rocks, as in they're pieces of pre-existing rocks. So sand grains would be the typical sediments that are going to make up a detrital sedimentary rock, for example. And I may have briefly touched on the 3 different types of sedimentary rocks in Chapter 2. I hope so. Anyway, detrital sedimentary rocks are typically going to have minerals such as quartz, feldspars, and clay. Limestones, when you find limestones, typically the mineral there is calcite, calcium carbonate. I did not write that down, but that's what the limestones are made of. Limestones tell you that that was a marine environment, meaning ocean water. Evaporite minerals, like salt flats or gypsum flats, tell us that that was an arid environment in the past. Like it was a lake in arid region, then it dried up and left behind large salt flats or gypsum flats. Larger grain sizes, meaning gravel, pebble, cobble, and boulder, larger grain sizes needed higher energy, swift, fast-moving water to transport. Sand, there's different sizes of sand, but in general, sand needs relatively high energy. Not as high in energy as the larger grains, but you do need some water flow to move sand. Silt and clay are our smallest particle sizes, and they can be moved by very weak currents. Rounded grains have been transported farther away or further away. English majors can tell me which one that was supposed to be. Rounded grains have been transported further away from the mountains where the sediments might have first weathered out of the rock. Why do we say that? Because the rivers and streams are Mother Nature's rock tumblers, and the further away from the mountains these grains move, the more smooth they become. Angular grains have not moved far. So angular grains, that rock probably, or set of sediment probably formed in the mountains or very close to the mountains, like maybe the foothills coming off the mountains. All right, we're going to move to another table for me to sit and rest on. I have taught all day today, 4 classes before doing this. Okay, so mountains to the sea. So mountains are on the left, sea, or the coastal area, is on the right. Okay, so what happens to the size of grains? They are larger in the mountains and they get smaller as they move through Mother Nature's rock tumbler to the coast. What about the shape? They begin as angular, pointy, jagged up in the mountains, and again as they move through the rivers and streams down to the coastal areas, they become more rounded. And then sorting. Sorting is describing, do you have all the same grain sizes together, or do you have a mixture of grain sizes? So in the mountains, it's poorly sorted, meaning you have a bunch of grain sizes together. You may go from as high as boulder all the way down to sand, maybe even fine sand in the mountains. But by the time, so we call that poorly sorted, if you have a mixture of different, at least a couple different grain sizes in your sediment there. But by the time this material makes its way to the coast, we expect it to be well sorted, meaning that it's all roughly the same grain size, like it might all be sand. Okay, now we're moving into a different color marker, the black marker, and we're starting a big section here that we're going to refer to as sedimentary structures. Honestly, everything we will do for the rest of this video lesson is sedimentary structures, and it's all in the same color of marker. Okay, so sedimentary structures are important because they tell us something about the depositional environment. They tell us a little something about what was the environment like when these sediments were being deposited. So let's go through a few of these. A sedimentary bed is simply a single layer of rock with a distinct top and a distinct bottom. It's one layer. If you have more than one sedimentary bed together, you refer to that as strata. And then the bedding planes are the boundaries between 2 adjacent beds. So I have very simple drawings on the board today because, well, that's all we really need, and I'm running out of board space. But I have a drawing there of some layers of rock. The Charlie Brown Christmas tree there always tells us where the ground surface is. So each of those layers of rock is a sedimentary bed. You take it all together, there's several of them there, we call that strata. And then the line, the boundary there in between each adjacent sedimentary bed is a bedding plane. So we see beds, bedding planes, and strata all on this one drawing. All right, moving on. I'm going to change where I'm sitting. I'm going to move all these chairs around. Okay, our next topic, still in sedimentary structures, by the way, ripple marks. There's 2 types of ripple marks. So ripple marks, what are they? They are small ridges, you know, like small little mountaintops. How small? They're on the order of centimeters. Really, that should say millimeters to centimeters. They're small ridges that form perpendicular to water flow. We have 2 types. The first type are referred to as wave-formed ripples. They are symmetrical, as I have drawn there, And they're symmetrical because you have an oscillating current, which means back and forth. What kind of current is oscillating? Tides, high tide, low tide. So when you have ripple marks, say in fine sand, that is showing you that was a beach environment in the past, or it's just offshore, a shallow marine environment in the past. Our second type of ripple mark are the current ripples. And these are asymmetrical, as I have drawn there. Meaning they don't look as the same on one side as the other. And this shows you water flow in one direction only. And what kind of water flows in one direction only? Rivers and streams. In what direction does water flow? Downhill. That's it. It's not any particular compass direction, but downhill. So if you have ripple marks in your ancient rocks you're looking at, it tells you a little something about the water environment that they formed in. All right, moving on. Next we have graded beds. These are packages of sediment that are stratified or layered according to grain size. Which means what? That you have larger grains on the bottom and smaller grains on the top and intermediate in between. They form in something we refer to as turbidity currents, which are underwater debris flows off of the continental shelves. So I have drawn there, you see there in that stratigraphy column, we see two different packages of graded beds. So what does that tell us? That tells us that, you know, wherever we found this set of graded beds in the past, this was an offshore environment, and that we had at least two underwater landslides here that we see preserved in the rock record. All right, one more for this board. I'm going to move another chair. Remember to move them back when I'm done. I probably won't. Okay, still in sedimentary structures. Cross-bedding. Cross-bedding means what? It means that the beds, the layers, are not all parallel to each other. So I have a drawing up there. What do we see? We see some flat-lying beds on top, and below that we see beds that are at a sharp angle. And below that we see flat beds again, and below that we see beds that are at a really high steep angle. This is cross-bedding. Okay, so these are formed either, cross beds are formed either due to sand being moved around by wind or water. Okay, so this indicates the flow or direction of flow of ancient wind or water. Okay, so our best example here would be desert dunes. Large cross-bedded sandstones indicate ancient desert dunes. Imagine a desert, you know, like the Sahara Desert. You have an ample sand supply. You have a lot of wind because you have a lot of temperature differences to set up differences in pressure. The wind blows the sand around and moves it around. They're constantly shifting. That's what gives you the cross-bedding if they become indurated or lithified in the rock record later on. Next are mud cracks. Now, first we're going to say for mud cracks that the V opens up to younger strata. What does that mean? We'll kind of get into that in one of our take-home quizzes. For now, let's look at that drawing there. And we'll say that's just a bush. It's not a big tree there showing us the ground surface. This is a cross-section of an area in a relatively dry place, perhaps, that has mud cracks. They are cracks. They are openings in the ground. Is it possible for other sediments to get washed in and fill in those cracks and get preserved in the rock record? Absolutely. So what do mud cracks tell us about this environment when the sediment was deposited? Well, we kind of had these alternating moist and dry conditions, so it could be tidal flats from the past. And if it fizzes in acid, that says, yeah, tidal flats, got some calcium carbonate. If it doesn't fizz, it's likely more of a land setting. Mud cracks could be an ancient lake shore, they could be an old river floodplain, or they could be a playa lake that dried up in an arid region. Okay, moving now to a different board. All right. We're still in sedimentary structures. Trace fossils are a type of sedimentary structure. I hope that light glare is not too bad. There's not a whole lot else I can do with the blinds. Trace fossils. What happens here is that we have evidence of an animal or plant living here or moving around here. We have that evidence, but we don't have any remains of that animal or plant, okay? So this includes tracks, like dinosaur tracks, burrows, feeding traces. Very much related to trace fossils is this notion of bioturbation. That's our next bullet there. This simply means that the sediment has been disturbed by some kind of living creature. Generally, in the case of bioturbation, it's mostly it's going to be animals. Anyway, your sediment has been disturbed. You know, so imagine, I don't know, prairie dogs. You know, prairie dogs make their home underground so the coyotes and any wolves that are around can't get them. And these burrows and feeding tubes can get preserved in the rock record. We call it bioturbation. It's a type of trace fossil. Okay, moving on. All right. Again, we're still in sedimentary structures. So, your sandstones and your limestones can have a type of geometry that we refer to as blanket geometry or sheet geometry, which means it's flat and goes out in all directions, perhaps for large distances. These could be thick deposits or thinner deposits, but if they're basically like a big flat blanket or sheet, that is referred to as blanket or sheet geometry. Now, when it's sandstones and it's in this kind of big, broad, flat shape, that tells us that this was likely an ancient beach, or perhaps just offshore where it's shallow marine. If it's blanket or sheet geometry of a limestone, then that's a marine environment, ocean environment, of various depths, depending on the type of limestone you have. An example is the Castlehane limestone, which is down there near Wilmington. It's actually at the town of Castlehane, which is west, just a little bit west of Wilmington on I-40, or off of I-40. Castlehane limestone. I think we had a drawing for Castlehane limestone in a previous video lesson. Okay, so our sandstones could have shoestring geometry instead of blanket geometry. And I should have drawn shoestring geometry. I think I'm going to. All right, bear with me. I'm going to set that down and just do a quick drawing of shoestring geometry, what that's going to look like. Like sandbars or barrier islands. And blanket geometry, I'll do a quick drawing for that. It's just going to be large and kind of looking like a rectangle. All right, back to filming. Okay, so for the blanket geology, I have a very crude triangle drawn. Just saying, you know, something that is you know, flat. It could be thick deposits, and it goes out in all directions for quite a distance, as opposed to shoestring geometry. Okay, so the two little drawings there on the left in the purple, those are representing point bars, also known as sandbars, on ancient rivers. Your shoestring geometry might also represent skinny barrier islands, and that's what we see there on the right, a rather skinny barrier island. We refer to that more linear design there as shoestring geometry. A couple things left in this first video lesson for Chapter 6. Deltas. I will not spend really any time on deltas in this class. In the lab, if you're taking the lab, you'll learn a little bit more about it. If you were going to become a geology major, go get a master's somewhere like NC State, Chapel Hill, and then go work for oil companies, well, you will be looking for some ancient deltas in the rock record. At that point, they would become important to you. So delta, everybody knows what delta is, right? It's where the river meets the sea, like the Great Mississippi River Delta. So how they're going to look when you find them in the rock record, exposed on the side of a hill, or maybe you dug a trench there and found something like this. In cross-section view, it'll kind of have a lens shape. What do we mean by lens? Like a contact lens, which is what I'm trying to draw here. So you might have something that looks like this on the side of a hill. You have this lens-shaped deposit of fine sand, and it could be rather large, and it's sitting on top of marine sediments. That's telling you that you probably found an ancient delta in the rock record. Reefs. I will not really concentrate on reefs at all for this class. There's a little snippet of reefs here because it's possible that Dr. Farley might discuss reefs in the lab. Everybody knows what reefs are, coral reefs. Can you find them preserved in the rock record? You can. I went to a location in the Appalachian Mountains in eastern West Virginia where we found limestones in those mountains, which was exciting enough, but we found actual coral reef limestones as well. That's really cool when you find it and it's in the mountains today and it's very old. So reefs may be long and narrow or they may be circular. That's about all we're going to say about reefs for my class. All right, one last snippet here. I'm getting quite tired. Okay, just a little bit about microfossils. Microfossils are just as they sound. They are fossils, but you need a microscope to be able to see them. And while this can give you a headache, if you spend too much time looking down the barrel of a microscope, it's actually kind of fun. So microfossils can be very useful. For example, you might find in your sediment, ancient sediment or sedimentary rock, you might find that you have diatoms and radiolarians, which are tiny creatures that make their shells out of silica, Si, basically quartz. If you want to know what they look like, just do a Google search, diatoms and radiolarians. They're really neat looking. And these things, they're marine, and they tend to form in cooler ocean waters. You know, they're not necessarily going to be too many of these in the tropics. Cooler ocean waters. All right, another example of a useful microfossil would be foraminifera. And we shorten that and just call them forams. And these are little tiny creatures that make their microscopic shell out of calcite or calcium carbonate. And I looked at plenty of foraminifera under a microscope when I was in grad school at UNCW. And we were looking at some very old sediments on the Cape Fear River. Some of these sediments were as old as, say, 72 to 65 million years. Had still not become solid rock, but the sediments were there and we were studying them, and we definitely had forams in our sediments. So we know that this was actually offshore marine at the time that those sediments were originally deposited. So if you have forams for your microfossils, then that tells you that it's marine ocean water, but warmer waters. All right, that will do it for Video Lesson Chapter 6, Part 1.